Hello IB, 13F. We are getting into with intersecting lines, and this is going to be a relatively quick video since we're just kind of going over how do we actually find out a point of intersection. So if we're using a vector equation, saying that line 1 is being represented by the resultant vector equal to the position vector plus this velocity vector, and then we've got a second line. How do we actually wind up figuring out when they intersect? So we know that if two lines are at the same place at the same time, they're going to have the same position. So what we would do is set our components equal to each other, just like we've been doing since we first learned about how to draw lines. So again, setting our lines equal to each other. Now as a vector equation, it'd be setting the components equal to each other. So we would be setting A1 plus T times B1 equal to A2 plus T times B2. All right, so that would mean we would set the X components equal and the Y components equal, and then solve for our scalar T in this case. And again, that would just be whatever two vectors we have, trying to figure out what that point of intersection is. Now we can also look at the velocity vector. We can look at the angle between the vectors now as well. So if we look at the angle between the velocity vectors, then we can figure out, do they actually intersect? Are they parallel? So there are a few things that this will go into in the next section as well. But right now, just looking at when they intersect and if they do intersect, so we just set the components equal to each other. So looking at this example question 2, you have a parallelogram that's given to you with these 4 different lines. And our first job is to try to figure out realistically where would these lines go. So if you think that, so AB and AD, so we have this point A, which is going to be the -4, 6, because that's where they're both starting. And then this one goes toward B, this one goes toward D. If we think of A as being here at -4, 6, and we travel 7 units right, 3 units up, and for this one, we travel 1 unit right, 2 units up. So this is going to be D, and this is going to be B, which would make this one C. And if you notice, DC and AB, so here's CD and AB. They look like they are parallel to each other by this -1 scalar. And then these two, AD and CB, the opposite sides of the parallelogram, again, parallel to each other by a -1 scalar as well. So they're just traveling in opposite directions to each other. So again, a few things just to reinforce how the picture is set up. That would mean that this is at 22, 25. And we can kind of do a little guess and check and take a look at how these lines are related to each other to figure out where all these points are. So we know where A and C are already. And then B and D, since we have an idea of how to travel to get to B from A and to get to D from C, we could try to figure out what points B and D are. So for example, if I left point A at -4, 6, and I travel 7 units right, 3 units up, how many times would I need to do that? So what would be my scalar R in order to get to point B? So just an example here, if I start at -4 and I travel 7 units right, if R was equal to 1, then I would be at 3, 9. And then if R was 2, I would be at 10, 12. And if R was 3, then I would be at 17, 15. And if R was 4, I would actually be past 22. And since my parallelogram is set up this way, I can't really go past 22. So let's see if 3 works. So here we're just guessing that R is equal to 3. And then if I go from C down to B, I'm traveling -1, -2. So how many times would I have to take 1 off of my X component and 2 off of my Y component to get down and see if I actually match up with 17, 15? And that actually does happen if U was 5. So here my guess is that B is 17, 15, where R is 3 and U is 5. Those are my scalars. Now I could do this, again, this is what it's asking you to do in part B, or we could use a more strategic approach, which is using our vector, setting our components equal to each other. So for example, if I wanted to test, figure out what R and U are, I would want to set AB equal to CB. to see what this point of intersection is. So if that is the case, my AB is negative 4, 6 plus 7, 3R. So negative 4, 6 plus R times 7, 3. And I want to set that equal to CB, which is 22, 25, plus U times negative 1 to negative 2. And I'm just going to solve this like I would with any linear equation. However, I'm going to set my x component, so negative 4 plus 7r equal to each other, and my y component, so 6 plus 3r equal to 25 minus 2u. All right, so go ahead and pause here and try to solve for what u and r are, and I'll put up my work here in a moment as well. All right, so if we solve for u with our x components set equal to each other, we can sub in to our y components. That u value is 26 minus 7r, and then that allows us to solve for r equals 3. So if r equals 3, when we come back, 26 minus 7r is u, so u is equal to 5. So that actually supported both of our guesses from trying to find what point B was earlier. So similarly, go ahead and find out what your D point is, and go ahead and test using vector, setting your vector components equal to each other. All right. Otherwise, this is a wrap up for this section, and we'll continue with the next one. Have a great night, guys.